Hello everyone, thank you for coming to my presentation. Today I would like to present one of our work in the Center for Sustainable Road Freight Heriot-Watt University. The title is Long-Haul Logistics Using Electric Trailers by Incorporating an Energy Consumption Meta Model into Agent-Based Model. What I will discuss today is a part of an ongoing project aimed at evaluating the feasibility and the benefits of electrification in reducing greenhouse gas emission and analyzing necessary reorganization in the UK long-haul logistics system through agent-based modeling and simulation. The full scope of our project will include analyzing how the operators interact with their customer and with other operators and how they can cooperate to use a shared infrastructure such as a charging hub. Trailer operations are critical part of supply chains in many developed economies. In the UK, it is estimated that long-haul logistics contribute to 45% of all greenhouse gases emission from road freight. To reduce the greenhouse gas emission, we can fit a battery on a trailer and use it as an energy source for the tractor unit. Because the long-haul logistic is energy intensive, the battery size is considerably big and heavy, and hence the dynamics of the trailer energy consumption must be taken into account. Engineering approaches are able to simulate the amount of energy required by a single trailer to travel on a particular route. It can take into account, for example, change in velocity, elevation, and the trailer's weight. However, it is computationally expensive and inhibits us from modeling the interaction within the entire fleet of trailers. So our objective at this phase of the project is to propose a suitable approach for modeling representative energy consumption in agent-based model. And we do this by developing a meta model based on Google and Schneider to estimate the energy consumed by the tractor unit and the trailer per kilometer, and then to evaluate the benefit of electric trailers for long-haul logistic operation. This is done by incorporating the meta model into an agent-based model that represent the operation of a UK trailer operators. Road transportation is a popular application for logistic simulation studies. However, very few studies that focus on long-haul logistics, especially studies that employ agent-based modeling and also consider electric vehicle. With regards to agent-based modeling studies of electric vehicle, most of them focus on passenger vehicle and not commercial vehicle. And in most studies, the energy consumption is taken into account as an average number. Even though engineering models of energy consumption exist, we cannot use them in agent-based model because it will require a long running time. Therefore, in this study, we try to propose an approach to incorporate a more representative energy consumption into an agent-based model without significantly increasing the running time. And secondly, we demonstrate this approach using a case study of electric trailers implementation in long-haul logistics. In this presentation, I will demonstrate how we develop an agent-based model of a UK trailer operators, how we develop an energy consumption model for the trailer, and how we use the agent-based model to evaluate the benefit of a new electric trailer concept. In our agent-based model, we have three types of agent. The first one is customer agents. This includes companies or store who generate pick-up or delivery orders to the trailer operators. The trailer operators then assign this pick-up or delivery order to one of its depot or warehouse, and then the warehouse will select the vehicle to do the pick-up or delivery. To develop our agent-based model, we use a dataset provided by a major trailer operator in the UK, and this is what happened on each day in our simulation. A simulation day starts by randomizing the total orders received by each depot operated by the trailer operator. An order can be ambient, cold, or frozen, and the proportion of each type of order is determined based on the empirical dataset. After that, we decide how many pallets are in an order, and this is also determined based on the empirical dataset. And finally, we decide the pickup and delivery location of each order. These pickup and delivery locations are extracted from the historical order data from the trailer operator. Once we generate the order, then we must allocate this payload into vehicle and the vehicle into routes. This procedure is executed by every depot agent. The payload and route allocation procedure start by grouping the orders with the same pickup location. This is to avoid multiple vehicles visiting the same location. After that, we construct a grand route for each group using nearest neighbor algorithm. We then start by using one vehicle and incorporate new destination to each journey until its capacity is full. If one vehicle is not enough, then we assign another vehicle to serve the rest of the destination. After we allocate the payload and the routes, then each vehicle agent will deliver the order. During its journey, it will calculate the distance traveled, the time traveled, and the amount of energy it consumed. This is where we will apply the energy consumption model. This is the screenshot of our agent-based model, and it's run on any logic platform. We then compare our simulation output with the empirical dataset provided by the operator, and we can see from this table that what happened in the simulation is quite similar to what happened in reality. Therefore, the intervention introduced to the operator agent can have similar influence to the real operator. The next step is to develop an energy consumption model for our simulation. Our objective is to develop an energy consumption model that is relatively easy to integrate into the agent-based model, relatively fast if it is executed within the agent-based model. It should be able to estimate the energy consumption based on several known factors, for example, payload distance, travel time, and also it must be quite accurate. We began by developing a mathematical model of mechanical power required to move the vehicle. This mathematical model considers the vehicle speed, the air resistance, the vehicle mass, and road gradient, the rolling resistance, and gravitational force. We then convert this mechanical power consumption into electric power consumption and fuel consumption rate. We then parameterize this mathematical model using the empirical data and also the data from the literature. And then we use Monte Carlo simulation to generate the distribution of energy demand. If we use the mathematical model to calculate the fuel consumption of the historical route done by the operator, then we will get the distribution on the left, and on the right is the real fuel consumption distribution obtained from the operator's CAN bus data. Even though they cannot satisfy any statistical test, we can see here that both distributions are quite similar, particularly their mean. We then develop a linear model to estimate the mechanical power required and use it in our agent-based model. Here, we assume that as long as the trailer batteries is above 20%, then half of the mechanical power will be taken from the battery and half will be taken from the diesel engine. However, if the battery power is less than 20%, then the trailer will move using diesel engine only. Finally, we use our agent-based model to evaluate the benefits of a new electric trailer concept provided by one of the UK trailer manufacturer. The battery pack of the trailer is 170 kilowatt hour, and this table summarizes its benefit. So if our operators keep using their old trailer, then 1 gallon of diesel fuel can only be used for 7 miles. But if they use the electric trailer, then 1 gallon of diesel fuel can be used for 19 miles. So the conclusion of this presentation is that we have proposed an agent-based model of long-haul logistic operation, and we have used it to evaluate the potential benefit of electric trailers. We have also proposed a method to model energy consumption with sufficient accuracy without significantly increase the simulation runtime. And we have also incorporated electric trailer into our agent-based model and show that the use of electric trailer is very beneficial in reducing the amount of fuel consumed by the operator. Our future research will include incorporating acceleration and braking event into our energy consumption model. We also aim at integrating congestion model into our ABM. We also interested at analyzing other intervention such as electric road system or Pony Express system. On top of that, we are also developing a specialized modeling platform that can handle a large-scale ABM efficiently. We are also developing a design of experiment method that can efficiently produce robust solution. Thank you very much for your attention. I welcome any comments or question from you.